Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications. Chapter 6, Calculus Applications to Climate Science. In this video, we will examine Stefan-Boltzmann Law, Budyko's approximation, linear approximation, and bisection method for solving nonlinear equations. Let's begin. First, for Chapter 6, you would need to import this list of packages so then we can compute all of the approximations that we are going to be looking at. Moving on to Stefan-Boltzmann's Law and Budyko approximation, we are going to be setting up figure 6.1, and first we are going to define the Budyko's parameters, namely A is equal to 212, B is equal to 1.6, EP value of 0.6, SG value of 5.67 e to the negative 8. We're going to set up a time line space from negative 50 to 50. We're going to set up an S variable, 1365, and a alpha variable equal to 0.3. Next, we are going to plot the data. We are going to plot a black line versus t on our x-axis versus a plus b times the value of t on our y-axis. This will be labeled as the Budyko radiation formula. For our second line, we're going to plot t against the equation EP times SG times the quantity of 273.15 plus T all to the fourth power. This will be in a blue line and have the label Stefan-Boltzmann radiation law. For the third line, we are going to plot T against the formula 189.4 plus 2.7 times the vector of T. This line will have the label linear approximation of the Stefan-Boltzmann law. That's going to be that SB. Lastly, for our last line, which is going to be in red, we are going to plot t against the value of 1 minus alpha times the S variable divided by 4 times the repeated measure of 1, the length of t. So this NP repeat is going to create a vector of 1s that is the same length of t. This line will be in red and have the label of observed outgoing radiation. Next, we're going to add some line labels, just indicating specifically what each line means. We have our Budyko formula, we have our Stefan-Boltzmann law, we have a linear approximation of the Stefan-Boltzmann law, and we have a line dictated as E out, which is going to be the outgoing radiation, which is equal to the value of 239 with a units of Wm squared on it. Then we're just going to modify some of the plot parameters, set the title, set the X label, set the Y label, set the Y limits, and go ahead and use the legend that they use in the Matplot library. We have a location of the upper left and a font size of extra large on that legend. We do get this beautiful figure 6.1 to pop out. Very busy plot, but we can clearly see that we have our outgoing energy in red, Stefan-Boltzmann law in blue. Our Budyko formula is going to be that black line, and our linear approximation of the Stefan-Boltzmann law is a purple line. Moving on to linear approximations, we are going to be finding the linear approximation of f of x equal to the quantity of 1 plus x to the fourth power, using the linear approximation dictated by L of x equal to 1 plus 4x. We're going to produce a table using f of x and L of x and observe the errors that arise when you use this L of x linear approximation. First, we're going to set up our x linspace. Then we are going to write a f of x as a list from 1 to 8. This is just going to be a value list. Next, we have our L of x list looking very similar, and E of x also repeating that list of ranges through 1 through 8. Now we enter into our formula and we are just going to add our actual values into each of these functions. For our f of x function, we have plotted that 1 plus x to the 4th power. For our L of x formula, we have mapped out 1 plus 4x. And for our error formula, we are rounding our f of x and then subtracting our L of x line and dividing by the f of x times 100. This will give us the error percent. Then we do want to set some options, so we want to display all of the columns in our data frame we are creating, and then creating our data frame using that pandas data frame function. We have our x value, our f of x values, our L of x values, and our error percentages. We do get this beautiful linear approximation table to come out. Using these x values, we have these f of x values, which correspond with these L of x values and have their corresponding error. Moving on to the bisection method for solving nonlinear equations, we're going to go over 2 examples. First, example 6.2, which we are defining a function that has one parameter x, and it is going to return x to the 3rd power minus x minus 1. Using the optimization package, we're going to go into that package and use the bisect function to find the root of this function between 0 and 2. We do in fact get one root out in between that bounds, and that is namely 1.3247. For example 6.3, we are approximating the EBM formula. We need parameter S set to 1,368, parameter EP equaling 0.6, and parameter SG equaling 5.67 e to the negative 8. We're going to define function 2, and it is going to have one parameter, and namely t value. We're going to return this EBM formula, which is dictated by the highlighted formula. EP times SG times T to the power of 4 minus the quantity of 1 minus the quantity of 0.5 minus 0.2 times the inverse tan of the quantity T minus 265 divided by 10, multiplying that entire quantity by S divided by 4. Using that optimization bisect function again on our F2 function, we are looking for roots in the bounds 270 to 300. We do receive one root within this range, and that is going to be 289.3089, roughly. This concludes part 1 of Chapter 6, Calculus Applications to Climate Science. Join us next time for the Newton's method and higher order derivatives.